Okay, is the volume okay? Good morning. Welcome to the Voices of Progress panel. I'm your host, Bethany Goldblum. I'm an associate professor in the Department of Nuclear Engineering. I'm here at UC Berkeley, and it's my pleasure to welcome you all here today. And for those of you joining us online, welcome as well. Thank you for being here. We're glad you're here. So before we get started, I just want to take a moment to recognize some of the folks who've worked to help make this event possible. So first, our chair and professor in the Department of Nuclear Engineering, Max Frattoni, and then also Rebecca Abergel, who is a professor in nuclear engineering and the associate dean for inclusive excellence in the College of Engineering. Thank you for making this opportunity possible. And then I also want to recognize Adriana and the Citrus team too for their support with AV and logistics. And then finally, I want to recognize Carolyn's son. She's there in the back. Carolyn is a research assistant in my group, and she also helped with organizing and fielding this event. So thank you so much, Carolyn. And then I want to give a special welcome as well to the students from San Jose State University that made the trek over here. Thank you so much for being here. So this panel is part of a series that's led by the Nuclear Engineering Department Heads Organization, NEDHO. And it was originally launched in 2022 by the University of Tennessee, Knoxville, with the aim of attracting a diverse talent pool to the nuclear engineering profession. And then since then, there's been events held at the University of Michigan, at the University of Wisconsin-Madison, and then we're very excited to bring you this panel today, which is aimed at exposing undergraduates from a variety of different majors and backgrounds to opportunities for graduate studies and then hopefully a career in nuclear engineering. And so with that, let's go ahead and get started. We'll start by asking our panelists to introduce themselves and just say a few words about who you are, what you do, and why you do what you do. And so we'll start here at my left.
Hello, my name is Tomi Kindle. So I'm a staff scientist at Lawrence Livermore National Laboratory. So a lot of the research I do is mostly focused on advanced detector design for various applications in nonproliferation, whether it be advanced reactor safeguards or emergency response. And I think we also have some projects for like treaty verification. And so the reason why I do this is, originally I was really interested in nuclear engineering specifically because of how it ties into clean energy production. But I'm quite a bit older than everyone. So by the time I was a sophomore in undergrad, the Fukushima Daiichi accident happened. And so this idea of a nuclear renaissance kind of fizzled away. And so I went more so into the, nuclear security route or nuclear safeguards route. And what's nice is now there seems to be this reemergence of advanced reactors, or I guess what was originally the nuclear renaissance seems to be more likely today. And it's a nice way that you can still tie back to your original interest in nonproliferation to start looking at, what are the new challenges posed by a new fleet of reactor designs.
So my name is Lee Bernstein, and I'm a professor here in the Nuclear Engineering Department, and I'm the Nuclear Data Group Leader up at Lawrence Berkeley Laboratory, which is just up the hill. And so how did I get into this? I guess that'll come later. But what am I doing? I'm doing way too many things. My group does work in fundamental science for the production of medical isotopes, for nonproliferation, for nuclear energy, and for space exploration. So because we're a nuclear data group, we try to measure the data that are needed for all of those applications. I'm just one person up here, but it's a group of 14 people, a mixture of students and staff that are working on those things. And I can't give a beautiful, succinct description like you gave over there, because there are so many different things that we're doing because nuclear is so incredibly valuable so broadly. Everyone thinks about reactors at first, but actually the truth is nuclear technology, it is the highest energy density, practically accessible form of energy around that we can use. And so, so it's got many different applications that can help with the betterment of human life.
So my name is Tatiana Sierra Perez. I'm a PhD student here at UC Berkeley, working with Dr. Fertoni, and I'm towards the end of my degree. I've been working on advanced nuclear reactor design, and specifically my thesis was on the new triso fuel particles that you have maybe heard that is going to be used in advanced nuclear reactors, and specifically characterizing their operational conditions during normal and accident conditions. So we get more informed about all the operational aspects that can happen to the fuel and characterize it. My undergrad was in physics. I did it in Greece, and I came here at UC Berkeley because I wanted to do something that is more applicable from nuclear physics to the real world applications. And that's why I was fascinated with nuclear reactors that are actually being designed and deployed right now. And you mentioned about the Renaissance. And for me, it was like, wow, I want to be part of this because I really believe in nuclear energy and how it can shape our energy mix in the future.
Hello, my name is Anthony Vasquez. I'm a second-year PhD student here at the Nuclear Engineering Department. My background is in physics and math at St. Mary's College of California, which is across the hill here, so pretty close. Currently, I work at the Bell Center in the IP2 team that's underneath the petawatt system, and there I'm currently working on a project of creating a new generation of plasma mirrors that will be used to increase the energy that is placed into our target area, and to then increase the energy of ion acceleration to, as of right now, practically be used to understand the behavior of, say, proton therapy, and even flash therapy is what we're hoping for in the coming year. So that's been something that I've been working on for about a year now. As for why I work in that specific area, my main motivation honestly came a year ago when I discovered the medical physics program at Berkeley, and that was a legitimate pathway for my PhD. As somebody who grew up in a cancer research facility up until I was 18, having a vessel, I guess, to understand different forms of radiation therapy, and to not only do that, but also maybe even characterize it further, and to then improve that science, and then go into the field of treating other patients, or even doing my own research later in life has been probably the most gratifying thing I've been able to find so far. Yeah.
Hello, everyone. My name is Jisoo Park. I'm a third-year PhD student here in the Nuclear Engineering Department, working with Professor Kai Fetter. And currently, I'm working in two projects. The first one is with the Applied Nuclear Physics program up at LBL, where we develop detector systems to be deployed in city environments to detect illicit nuclear materials in the city environments. And the second research, which I just recently joined, is with the Radiation Oncology Department at UCSF. And here we try to develop a new SPECT collimating system to decrease patient dose while scanning. And the reason why I ended up in these two research is basically I was interested in these two topics, interestingly, from my undergrad, so I'm from Seoul, Korea, and I did my bachelor's and my master's degree in Korea University. And my major was health and environmental science. And this department has like diverse professors with many different fields. And the two different topics was medical imaging and radiation safety. And Berkeley Nuclear Engineering Department had opportunity for me to just explore both of the topics, and here I am doing both of them.
Great, thank you. And so It was great to hear about the undergraduate studies from some of you. Did anyone else want to say anything about their background in terms of your work experience or your undergraduate area, and how, especially if that might be different from the traditional path?
So as an undergrad, I was a physics major as well. That's not unusual. There's lots of physicists who become recycled nuclear engineers. But I think part of my background that was unusual, and I tell students about this in all the classes that I teach, is I am first generation college. More than that, I grew up in a poor family. Everyone in my neighborhood, we were all. This was at a time when there was more opportunity, I think, available for young people than there is now. But certainly I had no idea what opportunities were out there in terms of nuclear. And in fact, if you had told me that I was going to end up being an engineer, I would have told you, oh, I don't even really like trains. Okay, like I had no idea what that was. Even when I went to college, I had no real understanding of what engineering was. And the reason why I was able to get started on this path was because of wonderful people who I met along the way. In particular, the woman who became my thesis advisor, Professor Jolie Jezewski at Rutgers University, took, which by the way is the state school in New Jersey, Go State Schools. Okay, she was somebody who I could understand and identify with. She too grew up in a working class or poor family, and she made me feel like there was a space for me to do this work. And so when I met her, she said, come and do your PhD with me. I said, well, isn't nuclear sort of dead and over? Physicist. And so I thought everything was highest energy. And she said, no, there's still some interesting work to be done here. And so really it was finding the right person for me that was so important. And I urge you all, look for that person, a person who's not just smart and compelling and interesting, but also kind. I think that's really important in any field.
Was not in nuclear engineering, so I started undergraduate studies in chemistry and math. And then I didn't really know what options were available in nuclear. And I attended the ACS Department of Energy Nuclear Chemistry Summer School, which was hosted at San Jose State University. And that was how I got exposure to nuclear issues, and then eventually ended up in the nuclear engineering department here. So tell us about some of the research areas that are within the field of nuclear engineering, and especially tell us about what is exciting you. If you want to talk about a specific project, we welcome that. And let's start now with Jisoo.
Of the two projects that I introduced. So especially for the first one, this was the first project that I worked on when I arrived here as a PhD student. And I told you we deploy different networks detector systems in the city environment. And in our case, there's actually 14 nodes, which is like 14 different radiation detection systems that are deployed in downtown Chicago. And the role I had for this project was to analyze different radiation background patterns for different locations in the city. And this was very interesting because the nodes that were like deployed near the medical district, and the nodes that were deployed like near more like where more cars are, where more like industrial stuff are going on, had very different radiation backgrounds, patterns. And the one thing that was really intriguing was that we could see the radiation patterns, especially in the medical district, that follows patterns for how hospital like treats patients. So for example, when we looked at F18 isotope signatures, there were high isotope signatures like within the daytime of the days of a week, but then we don't see any patterns in the like the weekends where they don't do any medical treatments. So using these different types of temporally and spatially different radiation background, we can like set a a better standard for like what is normal in the radiation background in the city environment. And that could help us to find out what illicit sources there are in the urban environments.
For my project specifically, what excites me the most about it is just how sort of new that sort of science is in terms of creating a plasma mirror from a liquid crystal. And the reason why it's exciting to me is because it actually, that component is probably the biggest part that's going to be placed on the back end of our laser system to then create higher energy ions or even electrons. And in sort of the 5 to 10 year plan that we have at the lab, we're actually very, or at least the theorists and now the experimentalists are very excited on the idea of potentially making or a collider or having data that can back up sort of plans to then create a collider. So that when that plasma mirror that I'm creating is going to then be duplicated into, say, several stages. Honestly, it's going to be in the hundreds in order to make a collider, but that goal of having a laser plasma accelerator that is so compact as opposed to what people typically think about colliders is honestly mind-blowing to me when you look at the sheer scale of the Bella Center that we have, which is, you know, very exciting for, you know, personally. Although another area in nuclear science that's very exciting that our group is also doing as well upstairs is working on nuclear security work. So one of the plans that a group has that we're creating a new laser system that will be even more compact what we have. And the main goal with that is that it'll be able to create muons that will be able to penetrate further deep into, say, cargo ships, or you could even, you know, you could have your laser system even farther away than what you normally, you know, would need to in order to detect, you know, nuclear devices in cargo ships to protect, you know, obviously civilians or different areas of the world. And so that is also a new project that's coming up for us that's, you know, very feasible. There's been numerous presentations for that in the lab. And so that's, you know, that's pretty exciting for me at least.
Yeah, so what excites me is all the development and design and exploration that is happening right now in advanced nuclear reactors and the different applications that this is happening for. So it's not only traditional energy for grid for using in your home to cook or to have electricity. It's also for like data centers, hospitals, remote locations, or emergency reliefs, or even space exploration. So all of this momentum that is right now happening in this field is very exciting and motivating for a young engineer like me. And when I first came here, actually as a physicist and focusing on nuclear physics, engineering was something completely new to me. I didn't know the application part of it. So I had the opportunity to work on a capstone project with 6 more people who had different experiences. Some were coming from Navy, some were coming from industry. And we put together a project that was designing a molten salt reactor, which is a low power molten salt reactor, which is one of the new designs, to create medical isotopes for cancer treatment or for diagnostics. And that was just mind blowing to me because I had the first experience to like design a nuclear reactor, which I hadn't ever touched before. And then I was working with people who had experience in the thermohydraulics part. So they were doing like the whole cooling system. Some people were working on like the business side of things or the medical side of things. And for me, like just having my hands on a project like that, which has a real application, but also at the same time, like having the freedom to make a new design and thinking out of the box. And this design has not been deployed. Some companies are searching to do it. But just having that opportunity to think out of the box and do something new is just very fascinating for me.
And just to follow up on that, there was an exciting announcement was it yesterday or today that Google has partnered with Kairos Power to build reactors to support their data centers. So this is nuclear helping to sustain those data centers, which is really exciting.
You want to say, what about my work excites me? Look at these folks, right? Just listen to the diversity of the use that you can find for nuclear technologies. So really, I mean, this is why in the end, I should say I was at Livermore for 22 years before I came here. It's because of young people like this and all of this great research that you're doing. I mean, and how incredibly important it is for human welfare. So, but for mine, like I said, I'm doing too many things. Let me get a show of hands. I can talk about fusion, fission, or medical isotopes. You want fusion, raise your hand. Okay, wow, that was so strong. Fission power? Okay, I'm sorry, fusion seems to be weak. So, and how about medical isotopes? Oh man, now I have to kind of poll you. No, I think fusion got the most, and it certainly got the most enthusiastic things. So I guess I'll talk about that. Okay, fusion research. So, you know, raise your hand if you've heard about the recent achievement of ignition at the National Ignition Facility. Yeah, I mean, this is a NEDHO thing. It makes sense that you've heard about this. That is an amazing thing that just happened. For the first time, we created a cell-sustained burning plasma, nuclear burning plasma without using an atomic bomb. Okay, that is a game changer. And it's really rather amazing. And for a moment, a gratuitous plug for, I had the privilege of working with one of the lead designers for that, Annie Kreitcher, who did her PhD with me when I was, she didn't do her PhD with me, she did her postdoc with me. Okay, so the big challenge, if we're going to take this amazing accomplishment and turn it into power, I think one of the single greatest challenges we're facing now isn't getting ignition. We got that, okay? Even though a lot of nuclear people don't like it that we did it with ICF instead of MCF. The big challenge are the neutrons. A gigawatt fusion power plant will be generating 53 grams of 14 MeV neutrons every day. I want you to think about that. It's going to need 160 grams of tritium every day. And how many folks are going to be worried about that? I know I am. Okay, that's a lot of tritium. Okay, and by the way, you can do other things with tritium besides make power. And so I think the great challenge for us now in nuclear fusion is to deal with the neutrons. First of all, they have 80% of the energy. We need them to make the tritium. If not, it's going to be a very short fusion energy program because we're going to burn up everything we got and that's it. Okay. And it is, I think, a marvelously and terrifyingly intense neutron field that you're dealing with there. And that brings a bunch of challenges in terms of activation and materials damage, gas production, and metals. These are things that I would never think I would have been doing before, but when you're in engineering, you learn to adapt, to find where the challenges are and figure out how to address them. So we happen to have, I believe this statement is true at this moment, although it's for a very small volume, the world's most intense fast neutron source just up the hill at the 88-inch cyclotron. And so we have been working with people at the NIF, as well as folks from several other interested fusion parties to start performing irradiations of material to try to develop techniques to mitigate the damage that you're going to get with 14 MeV neutrons, and also produce tritium. And we've also just started installing a DT neutron generator using something called associated particle imaging down in the basement of Echeverry. There isn't actually a basement, it's the first floor. And so I think watching us respond to this new challenge now that came up relatively recently because of that, that's a lot of fun. And it's watching young people being extremely creative and very hardworking. And I also think neutrons are really amazing. I don't know why, but I do.
And so I guess if I were to break up two of the things that I do, so on one end, looking at these emerging nuclear fuel cycles and understanding what are the proliferation risks and also the inherent proliferation, I guess, resistance to them. So one of the offices that I support is the same office that did the high enriched uranium to low enriched uranium conversion. And so right now, we don't have any non-nuclear weapons countries with high enriched uranium reactors. And so something they were really interested in for both fusion as well as advanced reactors is what should we be thinking about now so that we don't have to go to every country in 20 years and try to remove these reactors? And so there's this large interlaboratory study on nonproliferation resistance. So what are the inherent features of these advanced reactors that would make them proliferation resistant, so we don't have to worry about other countries having them if they were to remove themselves from some sort of like international agreement. And then in the same vein, we also are looking at appropriate safeguards related activities that we would need for these new fuel cycles, given the fact that they, when you have a molten salt reactor or pebble bed reactors, they completely change the paradigm of international safeguards that we're used to when we have, large fuel pins and assemblies. Now you have fuel that's non-quantized or heavily quantized to the point that they might as well be non-quantized. And so how can we actually track nuclear material, within reason? And then the other set of projects I work in, I kind of joke around that my job is really trying to understand what's in the box. So when I'm looking at some of the work that I'm doing for treaty verification, I'm trying to understand what's in the box, right? So if you have two countries that are in some sort of agreement together to reduce nuclear arms, right? You want to make sure that what they're dismantling is in fact a nuclear device, right? Not something else. But you also don't want to reveal sensitive information. So in that case, what are, inherent signatures of certain materials to ensure that, a device is actually being dismembered or disassembled. And in that case, when you're looking at treaty verification, you really have to look through very detailed information about a treaty, right? So when you're doing R&D, they tend to let you be more open-ended about what you're exploring. But when you're starting to do these things for, specific treaties that they're envisioning or specific treaties that they're interested in, there's an entire, letter of law that you literally have to follow. So if you were to read the New START Treaty, it's actually only 4 pages, but then there's a large appendix that goes into great detail about what technology can actually be used for, verifying that, a strategic device has been removed from some sort of aircraft carrier, et cetera. And so that's a highly constrained environment because, again, you have to fit into a treaty that's been negotiated between 2 different partners. Then when we have international safeguards, again, still constrained because, again, your end user there is usually the IAEA or some other verification body. And so in international safeguards, you're ensuring that nuclear reactors are effectively being used for, the reason that they're intended to be used for producing power, and that there's no nefarious activity, either from diversion or misuse that's going on. And so how do you quantify the fuel that's coming in? How do you quantify the fuel that's going out? And then again, with molten salt and pebble bed reactors, how do you quantify the fuel that's recirculating and doing it in a way that you're not intruding with the operations of that facility? And so again, when you're developing technology for a verification body, they tend to already know to some extent what they want. So a lot of times the things that you're developing might not be as revolutionary, more so like evolutionary, so small changes to existing technology or even algorithm development that might speed up the amount of time that would take for someone who's verifying this material, or things that would make their operational experience better. And then the last one would be emergency response. And so in that case, when you're trying to understand what's in the box, you have a lot more freedom because, if there's something concerning in the box, you want to make sure like, is it S&M or special nuclear material? Is it a criticality safety? Do you need to evacuate people? And so just given, the nature of that environment, there's a lot less regulations involved in terms of what you're developing and what can be used. But one of the things I would say, at least in the emergency response sense, in terms of the detectors that you are developing, you do also need to think a lot about the operational use of them, right? So is it lightweight, or is it so heavy that you need the only guy that can bench press 300 pounds to be the one that's deploying this detector, right? Sometimes people might have to be doing a search, and so they're walking around for miles, right? So is it something that's suitable for a human to wear for long periods of time? And if I were to look at, these projects, one of the ones that's probably the most gratifying is the multiplicity counter that we're currently developing for emergency response, only because it looks a lot at, a large aggregate system of fission events. And why that's interesting is my dissertation was actually looking at neutrons for nuclear data. So using a surrogate reaction to look at neutrons emitted from fission, as well as like the dreaded end-to-end cross-section. Well, yeah, if you can figure it out, yeah. And so it was just interesting looking at how the same techniques that we had done for something that was more nuclear data and then, nuclear physics related is now being used, in the field for something that is more applicable. And so, instead of like a large gadolinium doped tank that we had used, it was about like 3.5 tons, we now have like a 20-pound detector that, has lithium doping. So it's a lot easier to actually see the reaction. But again, it's a lot of the same techniques, but just different use cases. So.
I just want to pick up on something that Tomi just said. The real wonder about nuclear science and technology is how intertwined all of these things are. So the dreaded end-to-end cross-section that Tomi was referring to was something that we needed to know in order to maintain the safety and reliability of our nuclear stockpile in the absence of testing. This was work that I had done when I was at Livermore. That necessitated to measure that cross-section to allow us to get that level of confidence in our weapons. It necessitated using fast neutron sources. That stuff led me personally onto this quest to better understand the way that we generate fast neutrons here through a deuteron breakup process, which in turn became a whole program of measurements for non-proliferation and now also for NASA, but also opened up a way to make this extremely promising radioisotope, which very few of you want to hear about, called actinium-225, which is then a treatment for cancer. And as a part of these same fast neutron measurements, which stem out from this, we had done cross-section measurements. This was something I did collaboratively with Max, looking at chlorine-35 NP from molten chloride fast reactors, that ended up developing a technique for use with another detector, which Professor Goldblum is using right now for non-proliferation. It is a wonderful, beautiful, chaotic spaghetti mess of interconnection between these different techniques and capabilities. That's what nuclear gives you. So energy is in that web, so is non-proliferation, so is national security, so is cancer therapy, so is tracking illicit materials in urban settings, so is developing the next generation of muon production devices using laser accelerators, so is all the advanced reactor stuff that you heard here. And all this stuff is interdependent. So what you really need to be able, because you don't know what the next challenges are going to be, but nuclear gives you those tools to address those challenges. Be open-minded, get into the project, but don't forget what you learned in that, because you're probably going to use it again in something completely surprising later on.
That's the thing that surprised me in coming to the nuclear engineering field is really how diverse it is in terms of the different types of research projects that you can pursue. So we couldn't fit every different type of activity on the panel because we would be overflowing. But one of the areas that connects with chemistry is also in the development and characterization of radiation detector materials. So for those of you that took analytical chemistry, you're probably familiar with scintillators and Jablonski diagrams. So these same scintillators, like organic scintillators, are really attractive for neutron detection. And then neutrons can be signatures of special nuclear material. And so having that connection of the chemistry, the physics as well to apply towards nuclear applications is something that's available here. So what role, and you guys already talked about this a little bit, but I'll just invite you if you want to say more, what role do nuclear engineers play in addressing global challenges? And I'll just invite anyone to speak up. GC.
So when I heard about like global challenges that are dealt in nuclear engineering, I came up with this 2 projects that I was involved in the past. The first one is, it was a summer project with some of the undergraduate interns in our group, where we tried to develop a mobile portal system. And this was because of the situation in Ukraine, where there were like safety issues around the nuclear power plants, having like a lot of dangerous materials getting out of the power plant. So, but because there were a very limited amount of materials available, we tried to develop a mobile portal system with just using a simple sodium iodide scintillator detector and with a Raspberry Pi system to just create a very simple system that can detect any type of radiation, like gamma radiation detecting system. So this could be one of the example for trying to address global challenges, especially in the war zone. And the second one is, what was I trying to talk about? So there's another project in our group, which tries to detect some of the landmines that are buried deep down in the land that cannot really be detected in some other way. So there was I think it was still a simulation research where we tried to mount a neutron emitter in the drone system so that when it shoots neutrons into the land, it interacts with the landmine material. And if that, so it's a neutron activation analysis, and using the radiation signatures coming out of the landmines, we can detect like the amount and the location of the landmines. So yeah, those are the two types, I guess, especially for like war situations.
I guess I can go next. I mentioned before about the group upstairs at Bella that's working on creating a very compact laser plasma accelerator to then be able to produce muons for nuclear security, essentially. That's, I don't know too much about what goes into the science for their specific group, so I'm not sure if I can speak too much on that. However, in terms of tackling a global issue, I think for a lot of ports and a lot of, say, border border stations where a ton of material is being crossed, and there may be a lot of material in bulk that are, hidden within, different cargo ships, for example, or different, trucks, for example. Like, there may be some cases where our current technology isn't able to penetrate deep enough, nor is it efficient enough to also penetrate deep enough into the material while also maintaining efficiency in their process. And so their project is geared towards essentially meshing those two advantages, being efficient and also being able to penetrate, fairly deeply into certain materials for security. So I know that's their goal. However, for my group, an obvious global issue would be just the treatment of cancer. Cancer, unfortunately, has, there are increasing efforts to essentially fight off against tumors, and there's been developments of different forms of radiation therapy. And my group specifically, the massive advantage is making it more cost effective, because as of right now, there's a handful of proton beam therapy centers that are commercially available across the United States. However, many of those versions of therapy are highly expensive, and there's just, not everybody's obviously going to have access to it, but it is an amazing form of radiation therapy. And a benefit of using laser plasma acceleration already is that it's very cost effective. It's a very cost effective form of particle acceleration as opposed to what's been conventionally done. So making ion acceleration actually viable and in the long term commercially available in places like Bella, for example, would, essentially make a bridge in between cost effectiveness and properly administering the correct amount of dose and correctly taking care of tumors that could be within somebody's body.
For me, I try to categorize things in 4 different brackets, if you will. So that would be first and foremost energy production, clean energy production. That is one big thing in our group, especially designing these new, reliable, safe, cost-efficient, advanced nuclear reactors. Not that existing nuclear reactors are not safe, but you're trying to make a new system that will have more applications. It will be more cost effective and more efficient. You get better use of the materials. So that's the bigger thing in my mind in the sense of climate change and dealing with increasing energy demands. I know a lot of effort is being in electrifying everything, but where is this energy coming from? Are we still using natural gas and coal to produce energy to charge our car, for example? So I think one big aspect in terms of like global issues is energy production, and I think nuclear can be a big player in this. And renewables are great, but I think they're not enough. And then I would say in our group also we can do some medical research. I think there's also like a lot of potential there for nuclear energy to do constant treatment and do diagnostics in medicine. And as I mentioned before, there was a project like we were designing a molten salt reactor for medical isotope production. So you can see like how cross-disciplinary nuclear engineering is in general. And then I would say safety and security. You see now with the war in Ukraine and diverting nuclear material from a nuclear reactor, this is also something that we can simulate and make sure that we can track where the material is, and doing analysis on the fuel cycles, making sure that we optimize the use of the nuclear fuel. So there's a lot of potential, but I will categorize them in 4 different brackets: safety, security, energy, and medicine.
So in terms of impact in the world, I'm gonna go with the medicine one right now that we've got. But I want to connect it back to something else that is getting kind of overlooked here. And that is that the basis of nuclear engineering is in nuclear science. I'm going to give an example of how that connects in. So my group, I never would have thought this would have been the case 6 years ago. But we now have 3 patents on a mechanism to develop, to produce actinium-225. Some people may have heard of that. I don't know. Have you heard of that? Has anyone here in the audience heard? Okay, good, of actinium. So this is arguably the most promising radioisotope for the treatment of cancer. It has a 10-day half-life. It decays by alpha, which means it deposits its energy locally. So it's very high dose. And so if you can target it, if you can create a chemical that targets a specific feature on a cancer cell, and you can connect actinium to that, you will kill that cell. And the neat thing about it is that afterwards, there's a quick chain of 4 alphas and it's done. So it doesn't travel around in your body causing damage. It's very promising. It is in one of the most unfortunate places you could imagine in the table of isotopes to try to make something. It's in the middle of nowhere. The closest thing is radium, okay, which is the isotope that Marie Curie separated out of uranium initially. And it turns out that the best way to make this, which is the method that we've been doing, is, hate to say it, Tommy, N2N. It's shooting 1 energetic neutron into radium and knocking 2 out. You then turn 226 radium into 225, which after 15 days decays into actinium. So we have a mechanism for producing that. We have an industrial partner that we're working with on this, North Star Radioisotopes, LLC. And we're looking at creating a capability to produce that radioisotope here in Berkeley using a cyclotron that we'd like to situate on the first floor of Echeverry Hall. So, but this is where I want to connect back into basic science here. So all those nuclear cross sections that you've heard us refer to, like N2N or neutron capture, which is important for understanding the origin of elements in astrophysical settings. All of those things, our ability to model and understand them relies on good nuclear physics knowledge. And so the other thing that our group does, and it's not just our group, but other researchers in the nuclear engineering department here at Cal, is to try to understand that underlying science. And it turns out that some of this stuff, it sounds really esoteric, but it supports all the things that you just heard here. So for example, one of the things that really matters is knowing the ability of a nucleus to absorb and emit gamma rays, which the rest of us would call color, right? That's what color is. It's the ability to absorb and emit light of different frequencies. Turns out we don't actually know that very well for nuclei. And our group is leading one of the first efforts to try to come up with a comprehensive database and an underlying model to understand this thing. The fancy name is called gamma strength function, but it's really just color of the nucleus. And so all of these things that you're hearing, sitting behind them is a piece of science that supports this. And the cool thing about doing nuclear engineering in an academic setting like Cal is that you can stay on both sides of that, right? So I can be a professor in a nuclear engineering department, but work in a nuclear science division up at Lawrence Berkeley Lab, just like Professor Goldblum does. And so we try, because our goal here is research as well. And so sometimes that looks very clearly applicable to addressing a human issue. And sometimes it's a little bit more hidden, but it's important science, and we need bright people with insatiable curiosity to go out and come up with the next way to answer these questions. So
One thing I would say is, as the human civilization, I guess, we've really come up with two existential threats to, I guess, just our way of living, really, or even just existence. And that's climate change, which is man-made, and then, the threat of nuclear war. So everyone else is talking about medicine, improving human lives and, your quality of life and how long you're living. But then there's also, I'm here to bring the doom and gloom, just because I might as well. And, one thing, even though I don't really work in the nuclear energy sector as much, one of the things that I was just like really impressed by as we're seeing this, boom in AI was this idea that, if we didn't really have this much advancement in nuclear that we're seeing today, they would be using fossil fuels or even natural gas to be powering their AI centers, right? And so the fact that, nuclear has really advanced as an energy platform to where we do see the development of SMRs, different types of reactors that are more safe, it allows, whenever there's big booms of different technologies that may require large energy density, for whatever their application is, it allows them to make options that are sustainable and that are also healthy for the environment. And I'm not really sure if this had been the case 10 or 15 years today, what they would be using right now to power these centers. And so that's something that, I really appreciate, the work Max Bertoni does and others, specifically in the nuclear energy realm, because it's something that, we're seeing today is a huge problem, is global warming. And then also, again, my family is from West Africa. So my parents grew up in Nigeria. And whenever we would go and visit, I remember that randomly the lights would just go off, right? Because there's not enough energy for everyone in the country, right? And I just kind of remember my cousins like making fun of me and my siblings, like, these silly Americans who just expect the lights to be on all the time, right? And so when it's the middle of the night and all of a sudden, you're in Africa and the air conditioning goes off, right? Or the fans are off, right? It's a pretty miserable experience, right? And so that like fatigue will like set in and compounds. And so your quality of life when you don't have reliable energy is really unideal, right? Like imagine going to school when you haven't like slept through the night for a whole week, right? And so when we start to think about the idea that, a country like Nigeria in 2050 will be the third largest country in the world, right? How are they supposed to have power, right? How are they supposed to do that responsibly? And so I just really, I'm really grateful for a lot of the advancements that are being done in nuclear energy that's really providing an opportunity for some of these countries to really transcend the energy ladder and not go through the phase of burning coal, natural gas, et cetera, and being able to directly have nuclear. And then on the other end, one thing that we need to be conscious about is really, when we look at nuclear weapons, right? The first nuclear weapon, was detonated on Japan. And then 9 days later, the last nuclear weapon that was used in an act of war was detonated, right? And so the fact that, in all of these years, we haven't had another nuclear device that's been used in an act of war is quite frankly remarkable. And one of the things that we can attribute that to is, the nuclear deterrent that is being upheld by a lot of the nuclear laboratories, but then also this idea that we effectively don't have as many nuclear players in the game that could increase the probability that a device is used. And on that same note, right, the countries that do have nuclear devices should be working towards, dismantlement, right, reducing the number of arms. So again, that they're less likely to be used in an act of war, which again creates an existential threat for, humanity. And so the technology that we work on at Livermore, at the National Lab, even here at Berkeley in the Nuclear Engineering Department, is really focused on, to some extent, non-proliferation and nuclear security to really ensure that we don't have to worry about that existential threat. So one thing that's nice about nuclear is that we really are entwined in both, man-made existential threats. And we could even talk about asteroids coming and wiping us all up. There's actually nuclear ideas for how to, solve that too. So, yeah.
Thank you, Tommy. Yes, that's really powerful. And I think it is an important opportunity for all of us to be able to work to reduce the risks associated with nuclear weapons and related technologies. So the last question I have for you all today, is there a key piece of advice that you would give for students interested in breaking into nuclear engineering, especially those from coming outside of nuclear engineering, so maybe didn't have a specialized nuclear program or didn't have access to traditional resources like internships in the field? What advice would you give those students? And we'll start with Tommy.
Yeah, I guess the advice I would give is to seek mentorship like early and often. I think about all the random things that I've done over the course of my career, and a lot of it has really been impactful or useful because there have been people who have been helping me, advising me, as well as mentoring me. And I think that when you can gain the experience of someone who's been in the field longer than you, then that's one way that you can really kind of break into the field a little better. And again, the mentors that you do seek can really be at any level, right? So it could be early or like, other graduate students, as well as like professors or even people in the field. And everyone would be happy to talk to you about like their experiences. Because I don't know anyone who doesn't enjoy talking about themselves, or maybe that's just me because I'm a narcissist, but people like talking about themselves. So if you were to ask, how did you get here? What advice do you have for me? Or, I'm struggling with this problem, how would you solve it? Or something along those lines. I think, people would be very happy to help you. Yeah.
I mean, that was my line from earlier. My thesis advisor, Joey Chizevsky, was the person that, but I'd grow it very slightly more. You do need to find a good person. You do need to find good mentors. That's important at all points. You need to find a community. I think that when you're young, that's really important. Okay, it's, biology has set us up for this thing. We are marvelously collaborative beings. You need to find a community. And one of the things that I like about nuclear is that it's just about the right side, is it's in that Goldilocks level where you can get to know lots of people. It's not so large like EECs are here. And yet there is a tremendous amount of opportunities to do different things and meet different people. So at all levels, you need that mentorship. That could be somebody who is literally just somebody you're commiserating with over homework, all the way up through maybe the person who is the graduate student who was teaching that class before, through to the next level, the junior faculty, the senior faculty, some people at national laboratories. You're also, whether you're from San Jose State or from here, you've got a couple of national labs right nearby. Take advantage of that. If you're elsewhere, find folks like that. The national labs are trying very hard to reach out and provide mentorship to the general community. You can cold email people and you'll probably get a response. Although if you don't, do it a second time, and then you almost definitely will. But community is as important as mentoring, that you have folks that you feel comfortable and happy chatting with, being with.
Yeah, I totally agree. And from my experience, just reaching out to people and cold emailing, and yes, you may not get every time a response, but don't let that discourage you. Just keep sending emails or like reaching out to people. And as is mentioned, like everybody likes talking about their projects and what they're passionate about. But I will also want to add, be curious. I think that was one thing that it was really helpful for me. Like when somebody tells you that you cannot do it, disregard. Just go with what is passionate. What makes you drive every day, and like what makes you wake up in the morning, and just be curious. Try to seek answers to the questions that you have. And right now, I feel like in this era, there's so much information out there, even if you don't have traditional resources, like going on the internet, and there are multiple YouTube channels or like free courses on Coursera or edX or whatever platform you want to choose. And you can start having fundamental knowledge, and then you can gain your way towards your goal that way. I think being resourceful, being curious, not being discouraged, and just be passionate about what you're doing, and keep asking questions, reaching out to people. I think it's very important. And I think I want to add something else, is the community, but also there was something else, but I remember. Okay, yeah.
I think it's not a coincidence that the common theme is diversity in who you know and what you know, from what, everybody on here has been saying. Me personally, like, I don't come from a nuclear background whatsoever. I originally thought I was going to be an astronomer. And then I cold emailed one of the staff scientists at the Bell Center up the hill, and within a day had an email back. Within 2 weeks, I was working at the lab. And it really is remarkable how fast, certain opportunities can happen. And I also think that when you don't know a lot about it, a lot of people tend to be scared, tend to want to prove to their mentors or their collaborators or their peers that they know what they're doing, when in reality you have so many questions. And I think, like, it's so important for you to have a diverse set of collaborators. And what I mean by that, I guess if you want to speak more from an academic standpoint, many people in my cohort in the nuclear engineering department come from chemistry backgrounds, come from electrical engineer backgrounds, come from, purely theoretical physics. Like, there's so many different people that I work with on homework, on like asking for advice on something that I'm working on in my project, and I still, like, they are my very close friends, and I still talk to them every day, or hopefully every day, if I'm not busy. But at least at some point, you need to have a diverse group. And there was one other thing I was going to say as well, but yeah, I just think the collaboration is very, very crucial, and asking questions, even when you don't want to ask them because you want to feel like you know what you're doing. In reality, it is perfectly okay to ask questions and to do that.
So I totally agree with the rest of the panelists to go look for good community, good mentorship. And one thing I do want to address is kind of similar to what Tatiana kind of said, is to look for resources outside of your like comfort zone. So there are things that I regret on my undergrad and some things that I am proud of. And one thing that I'm really proud of is that even though I didn't come from like an engineering department or like a physics department that could be relevant to nuclear engineering, I try to explore a lot of different courses outside my department. So I try to fill in the gaps from what I learned from my own department and with what I want to pursue by taking like engineering mathematics courses from MECI, going to bioengineering to take like image reconstruction courses. And I never knew that would all come into what I do right now, but like whatever you do, just do good, and everything that you do will in the end be helpful to what you do in the future.
Great, thank you. And so on that note, we've reached the end of our time here with the panel. We do have time, though, to continue the discussions. For those of you that are here in person, we're going to have a reception outside where you can chat, additional advice perhaps folks have, and then we also have chocolate-covered strawberries. But those of you joining online as well, we'll be reaching out to you with more information and to follow up on any of your questions. All, please join me in thanking our panelists for this great discussion. And thank you all for being here. Have a great day.